also continuously. But you cannot just took a set of data and then process it. And then you take a set of data and process it manually. That would be cost a lot of time. That's why we need this calculation actually for those purpose. If we have a lot of set of data which comes continuously and you need to what is it, to obtain the statistic, could calculate the average of those continuous data, and do it also continuously. Have a what is it? An updated statistical parameter for those data. Okay, that is just an application of this. And then for the classification of the systems, there are some some parameters which will give a characteristic of the discrete time system. For the first one, it depends on the memory of the system. What I mean is, if the system doesn't need memory, doesn't need a shift register memories, like I think I mentioned that also last week. The system is called memoryless. For example, for the example of a memoryless system is this linear system. Yn equals to half of xn. You can see clearly in here that the output of Yn only depends on the input at n also. So the output of Yn doesn't need anything that doesn't need any data who is coming from the previous time or the previous sample of data. So in here, on the contrary, so we have a with memory system. The example is this: Yn is equal to xn plus 0.2 xn minus 1. And here you can see that Yn depends on the input at current n, and depends also on the previous input xn minus 1. Yeah, so the system is memoryless if the output of the system is only depends on the data at n equals to n0. Yeah, so it doesn't need any memory. Okay, I think it is clear enough. So the next one, classification can be done based on the characteristic, whether it is a linear system or a non-linear system. And how do we know that if the system is linear or not? There are two examples here. For the blue one is for the linear one, so Yn is equal to half xn minus 1 plus xn minus 2 and so on. It is clearly a linear system. If you know linear system in mathematics, it is the same. The linear equation in mathematics, yeah. I suppose you already know about that, it is the same. So in here it is said to be linear. And also the condition, another condition here, we could say that the system is linear if the transformation of A times x1n plus b x2n equals to A transformation of x1n plus b transformation of x2n. So this means that if we have two discrete time signal x1n and x2n, and those signals are multiplied with a certain constant variable. In this case, A and B is the constant, sorry, not the constant variable, a constant, yeah, constant number A and B. So if we do a transformation, yeah, of these two signals added together, then the output of this transformation must be equal to the transformation of each of the symbol individually, then multiply by its constant A and B. So you understand the difference? So if we on the box, like, you could say that if this is the system, yeah, and this is the yn, and this is the xn here. If xn equals to x1n plus x2n, of course with the constant number here, okay, and this will become the input to this linear system, then the output yn must be equal to, when there are this one would be AX1N. We could say this output is Y1N. Then another one, BX2N. And the output would be Y2N. If the system is linear, then this Yn here must be equals to Y1N plus Y2N. Then you could set that the system is linear. And for the second example here, it is definitely not it's a nonlinear system, because you can see that this is a quadratic equation, that yn equals to x quadrat n, x in the power of 2 n. So it is definitely not a linear system. You could follow the discussion until here, or if you have some question, you could raise your hand, or you can ask away, yeah, before you forget your question later. So that is a linear system. Oops. Then another properties of the linear system here is whether it is time invariant or it is a time variant system. What it means that if a system is called a time invariant system, that means the system is not it's not changing based on the time. So yn is equal to 0.5 xn. This is an example of a time invariant system. The condition that the system is called time invariant is that if we do a transformation of an input xn at a certain time n0, yeah, or you could say a shifted version of xn, delayed n0 sample of xn, then the output would also equals to the shifted version of yn. It means that the system will be a time invariant system. If we compare to the second example, which is a time varying, time varying system, yn equals to n times xn. This, if you see for a shifted version of this yn, you would know that the result will not fulfill this condition, because if we see when yn minus n0, so wrote it down there, when yn minus n0 would be n minus n0 x n 0. So this part here, which will make the signal becomes time varying. In the real application, if you want to imagine what's the real effect if you have a time varying system, is like this. If you, for example, you are an engineer and then you have designed a system, yeah, and then for example, it is just a simulator. So you have done coding or some sort of, and then you make a certain simulator which simulate a signal probably, and then if you running the program, running your simulator today, and then it gives a certain output, for example, a certain output A, and then when you run the simulation tomorrow, you will get a different result and not equals to A. You can imagine if you have a system which the output is you cannot predict the output. I mean, you can predict the output, but we want to have a system, yeah, if we give the system a certain output today and a certain output and the same input we give to the system tomorrow, we expect to have the same result. Yeah, it's like when you make a dish, or you make what is it, a cuisine or something, or a bread or cookie or something. You have a certain ingredient, yeah, which is a fixed ingredient, yeah. For example, you have a factory for making breads or something, and if you give the ingredients today, yeah, and you you assume that the ingredient is the input of the factory, you expect that the output will be a bread with a certain qualities and with a certain amount quantities. Okay, but if the system is time varying, if you give the same exactly input as what you did today, but and you give it to this factory, for example, and the output of the factory will be completely a different kind of bread and a different sound amount of what is it, qualities and quantities, is everything is different. We don't want to have those kind of system. That's why when we design a system, yeah, we always want to have this time invariant system, because we want to know exactly what we would get, yeah, at uh, any time, yeah. Do you get what I mean for this uh, third classification of linear system?
Yes, ma'am.
Okay,
Yeah.
okay. So I can move on to the fourth one then. This is also an important classification, yeah, or the characteristic of a linear system. As a design, as a system designer or an engineering in this case, you have to make sure that your system is causal. Why? Because only a causal system that can be built or can be realized to become the real system. So perhaps you design a system which is very complex and very perfect, but in reality you cannot make this system. That would be useless. So you must make sure that the system is causal, so you can produce and make it in a real life. And how you consider a system is causal or not, or non-causal, it will depend on this condition. So the system is causal if the output at a certain n equals to n0 only depends on the input at n less than or equals to n0. In another way of saying, we could say that the output of the system only depends on the same of the input at the same time or the previous time. So the system is not the system do, do not depend on the, what is it, the next input at the future time. So for example, in this equation, the system is non-causal because of the last part of this equation here. This one, which make the system is non-causal because it depends on the time. If you see, this is like a fast forward system in this time signal. Yeah? This is a delayed version. This is a currently time, yeah, which is equals to the output at end here. This is the previous and this is the future, the next one. We cannot depend the output or sorry, the input at the next step into our differential equation here. Yeah. Because we cannot depend something that it's in the future. Okay, for this example, probably you could argue that we can do this if we exactly knew what is the next input. But if you, for example, this is not only depend on the input today, the last previous time, but it also depend probably for the next output. Can you imagine a system like this? This is like, you can make prophecy about what happened on the next one. This is impossible. That's why it for causal system, we could only depend on the input at a certain n, a certain time when n or equal to n0, not depend on something in the future, because there is uncertainty that we have to calculate, and we cannot predict what happened in the future. We cannot make a system which depend on something that we predict, that can be changed and can be, we cannot hold on that. That's why we need to make a system which have this characteristic as a causal system. And then the next important thing that we must make sure that the system that we design is stable. We used to call it stable BIBO, which is a bounded input, bounded output. Which means that if we have a system and we give a bounded input, then it must make or produce also a bounded output. Yeah. So we could say that the magnitude of input xn is less than infinite. Bx here is the bound of x. So it is like a limit of the value of the magnitude of xn here. And because it has a limitation here, so it is not an infinite, so it is bounded at Bx. And if the system that we design, yeah, is have an input which bounded like this, yeah, for all n values, then the output must be also a bounded output signal y when the magnitude of yn is less or equal than the limit by bound of yn. So you have to make a note here that this is the magnitude. Yeah. What is the bound, the limitation is on the magnitude value of the input signal and the output signal, and not for the n series. So this is happened for all n, yeah, but the bound is for the value, the magnitude value of the signal. Yeah. So this is the example of the the example of a unstable system is the new that the accumulator, when we sum up the value of xk here, yeah, from minus infinity to n, that will be then we will have the amplitude of this summation result. It won't have a bounded output on the yn part, because we knew here that the xk probably is not infinite, yeah, limited, but the yn is probably infinite, because yn is the summation of xk, and the value will be will getting larger and larger and larger, because it is a summation uh, of this series xk, and when the n goes to infinite, this summation probably will also result in an infinite number. That's why this system is an example of a non-stable system. Because probably in formula, in mathematics, we often have an infinite number of infinite series, but in the real life, it is difficult to handle an infinite number. Probably it's impossible to handle an infinite number. So if you create a system, you have to avoid working with an infinite number. You have to have a certain limit to make it easier to handle your system. So it will be a stable system and easier to handle. And then for the next one, this is what we will work on furthermore in this chapter. It is a linear time invariant system. So if you could see, in this linear time invariant system, then the system is a linear system and it has a characteristic where it is time invariant. So this is what we will want to design, or we will want to have as our system. Yeah. And then the next important parameters that you have to know, okay, which is called response impulse of a system, of an LTE system. It is notated with HN here. And what it means by response impulse HN here is that if we have a linear time invariant system which does a certain transformation here, and then we have an input xn and an output yn, we call the what is it, the output of this system is a response impulse if the input is a unit impulse signal. Last week you already know what is a unit impulse signal. It is the simplest kind of signal. Yeah? Where do you remember? What is an impulse, unit impulse? This is a unit impulse. This is an n. Unit impulse is equal to 1 when n equals to 0 and 0 for n not equal to 0. So it only has this number, yeah, this value of 1 when n equals to 0. This is a unit impulse. You must understand that this unit impulse is like an identity function. For example, you knew an identity function is like 0 in summation and like 1 in multiplication. So if you sum any kind of numbers with 0, you will get
0.
Come on, you will not get 0. If you sum up any kind of number with 0, what will you get?
The original input signal.
Yeah, you will get those same numbers. Yeah, if you multiply anything with 1, you also will get those same number that you multiplied with 1, which is called an identity function or an identity number. 0 is an identity number in summation and 1 is an identity number in multiplication. And this unit impulse here is an identity function in this linear time invariant system, which means that if you make this unit impulse as an input to a certain system, actually the output would describing the system itself. That is why it is important to understand and to know about this response impulse, because we could understand the system if we know the response impulse impulse of the system. Or we could say impulse response of the system in English. So it is a response or an output of this system when the input is an unit impulse. So if we want to know what the system do, you can understand it by knowing about the impulse response of those systems. Then how we could get this impulse response? This is the steps. For example, here we have an input discrete time signal xn, which is defined by this equation here. It is a summation of xk times del and min k, times del and min k, which is a shifted unit impulse, and xk is a number where k is range from minus infinite to infinite. So we could say that if LTI system is given an output xm, which is a delayed version of an impulse, an impulse, unit impulse, n min k, then the output of this LTI system would be its impulse response of the system. This is the variation of notation that you could use for defining an impulse response of the system. So in several books, they have sometimes they have a certain style of notation for defining this impulse response. Some books written it in this way: hk as function of n, and there is also a books which written in explicitly, which is hn min k, and then we could also set that it is the transformation of an input xn, which is xn is equal to del n min k. And if we relate it to the output yn is the transformation of input xn, and we knew that the xn will follow this equation here, then the yn will equals to the transformation of this summation here. Or we could say also that yn will equals to the summation of the transformation xk to n. This will bring to the next operation. Probably you are not familiar yet with this operation. So beside the summation, multiplication, shifting, we also have convolution in here. which define as in the form of mathematical formula. It is defined that the output yn equals to the summation sigma from k minus infinite to infinite xk hn min k. And this is what we call a convolutional summation. For simplified, usually we only call it convolution. So here it is the notation of convolution in mathematics. Usually we use this star or asterisk here. If xn convolution hn, and you could written it in this way. And if xn convolution with hn, yeah, in our linear time invariant system, yeah, our output yn will equals to xn convolution with impulse response hn. This will equal to the operator here, k min infinite to infinite xk time hn min k. That would be the formula for discrete convolution between an input signal and the impulse response of the system. By convolution of these two, we could get the output of the system. So you could calculate the output of the system if you know exactly the input signal, and you also have to know about the impulse response of the system. Okay. This is the properties of the discrete convolution. It is commutative. So if you convolve between xn and hn, and you change the order hn convolution xn, it will have the same result. Yeah. And it also have this property, it is associative, so it doesn't matter the order of the convolution, yeah, because it is a linear system. So if you have two systems, yeah, and then for the first system you have the input xn, and you can do the convolution here first. Then if this output of this system goes to another discrete system h2n, then you could also find the output of the system by, at first you do the convolution for the two systems, yeah, h1 and convolution with h2n. Then the results of this convolution, yeah, this is the resulting system, or what is it, the equivalent system. 1, and this is xn. Or you could also have this, where you did the convolution of the system first, and you take this input signal in. This would be an equivalent. Yeah. And for the distributive property here, if we have we have two systems to convolution, did convolution to between xn with these two systems, or we could do it the convolution individually to both of the system like this. If we could draw the system, it would be like this. For the blue one, we could, this is the input xn, and the input goes through wait a minute. This would be for the right one. That would be this system, yeah, and the right one, in the right part of the equation. And then for this one, yeah, you could only sum up this, and you give the input. This is also have the same value. And then for the identity order here, if you you do a convolution here, xn convolution with del n will equal to del n convolution with xn. And that would be equal to xn, because anything, any signal which is convolute with del n, it will be the same because of the identity property of that. And then the fifth one, if we do convolution xn with the shifted version of unit impulse, yeah, then the result of this operation here is the shifted of xn. Xn with del n, yeah, xn with del n will equals to xn. Nothing happened. It's just like multiplying xn with 1. And then if you convoluting xn with shifted of unit impulse, the result is exactly the same as xn, only that it is shifted k sample to the right. So the signal looks like what the signal look like. It's not changing. It is the only that it is shifted. So del n function did not change the what is it? It did not change the characteristic of the signal xn. For example, its amplitude will not changing, its frequency is not changing. Only in here, because it is shifted unit impulse, then the xn is also a shifted version of xn. Xn min k. Yeah, this is the sketch that I think I've done it. Properties. Yeah? So because you know about the impulse response, yeah, we could determine, yeah, whether the system is causal or not, or the system is stable or not, only by seeing the impulse. Yeah, it can be easier done if we knew the impulse response of the system, because we could determine whether the system is causal or not. Yeah, the system is causal if the impulse response Hn equals to 0 for n less than 0. If this condition is fulfilled, then you could say that the system is causal. That's it. You don't have to prove any other condition. Just look at the impulse response. If the impulse response equals to 0 for n less than 0, then it is a causal system. Easy. And then you could say that the system is stable also by seeing its impulse response. If the magnitude of the impulse response, the summation of the magnitude of the impulse response is less than infinite, which is mean it is bounded, it is limited, then you could say that the system is stable. Then next properties, based on its impulse response, you could classify linear system into two different types. The first one is a finite impulse response. Yeah. It is a discrete time system which have a finite duration of impulse response. Yeah. And then the second one here it is called infinite impulse response because the system would have an infinite duration of impulse response. So this what you could determine only by seeing the impulse response of the system. Yeah, so many things can you can determine only by seeing, only by analyzing the impulse response of the system. So it is necessary to understand and to know about this impulse response. So another one that you have to understand in the system will be characterized, or you could know the system by looking the relation between the output of the system and the input of the system, and it can be done by analyzing the differential equation, yeah? The n order of a differential equation, which has the general form as the following. So this one, you could see a differential equation here between the output of the system and the input of the system. So the left hand side here is the equation which is only related on the output at n equals to n0, yeah, or at a certain n value, and the right hand side of the equation, it is related to the input of the system, yeah. And then you also have to notice that the order of the equation, or the order of the system in this case, it is it depends on this n value here, the limit of the summation for the output of the system. You must remember the order of the system, it depends on this maximum, limit of the summation on the output equation, not in the input. Yeah, it does not depend on the what is it, the upper the summation of the input, but it's in the output. So if we assume that the system is causal, then we could simplify, or we could change this equation into the next one here. So how did it change from here to here, n equals to blah 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 here. So if we have this equation, we could one by taking out the yn value when k equals to 0. Yeah, you could see that in the next equation, the summation is not ranging from k equals to 0 to n, but from 1 to n, which means it can be made from this. We could take out for the k equals to 0, which this will be a0, y n minus 0 would be yn, and then plus sigma k equals to 1 to n ak y n minus k. This is the left part of the equation. I could write it down like this. It has the same meaning as this one, right? And then the next one, we have to define, because what we want to know is this output yn, output at a certain time value n, depends on what? On input at what time, and then at output of the previous time. We could say in general that yn will equals to this minus this, right? So it will become, because it changed the side from the left side to the, sorry, from the left, then you will get exactly the equation as the second one here, plus this part. Yeah. To m y, sorry, bk x n in k, and don't forget that you still have this a0 here. So a0 there must be normalized that the expression is explaining that yn, the output of yn will depend on the output of the previous time, output at current time and the previous time. Depend on current input and the previous one. This is what we call a differential equation for determining the characteristic of an LTI system. If you already have this equation, you could begin to draw the the planning of the realization of your system, where basically you could draw these blocks based on the mathematical formulation in this differential equation. So there must be an input xn, yeah, and then this, if we need another input, yeah, to make an output yn, yeah, this is what we call an adder element, yeah. So an adder is an element for sum up between two input signal. In this example, we have two input signal which determining the value of yn, which is xn and wn here. Yn equals to xn plus yn. Okay. This expression can be illustrated, could be drawn into a symbolize of an adder is plus and then a circle. Some books also have a different notation, or what is it, a symbol for adder, which is sometimes it is written as a sigma here. It is also to describe an adder in the block diagram. Basically, it shows what the input of a system and what's the output of a system. This is an adder for summation of the input. And then the next one is a multiplier. We also need a multiplier because some systems have a constant multiplier given to its input, and it is described or symbolized with like a triangle here or like an arrow. Some books just symbolize it as this. You can also draw as multiplier. Then yn will equals to a times xn. There is also which describe it as a small triangle here. This is a multiplier element with a constant value, which is written on the upper of the triangle. In this case is upper of an arrow. And then the next one is a shift register or a delayed element. Usually it is described as a box with a z minus 1 symbolize that it is delayed one step before or one sample before. This is to illustrate about the memory of the system. Yeah. So if you put input xn through this shift register, the output of this shift register would be xn minus 1. So it is like delayed xn one step before. One step. Yeah. So if you need to store the value of a previous input, you need to have this memory to store the value. And if, for example, you need not only xn minus 1 value, but you also need xn minus 2, for example, then you would need another shift register, something like this. If this input is xn, entering the first sub shift register and then the second one, in here xn would be xn minus 1, and then if it is shifted furthermore here one step more, and then the output here would be xn minus 2 and so on. Yeah. This we could combine these elements and make our system. This next example here. Now, we could combine all the elements to create our whole system. For example, we have a system which described with differential equation yn equals to b0 xn plus b1 xn min 1. We could see that we will need a shift register based on this knowledge here. And then we will need a multiplier because of this constant number b0 and b1. Yeah. And then we have the input xn and the output yn. We could draw our diagram. If this is the input, yeah. Yeah, Kahari, you have a questions?
I do have a question. So, can a multiplier accept two inputs? Say in this case, what if I wanted b0 times x of n plus x of n minus 1? Can it be like that?
If b0 is, sorry, can you repeat?
No, can a multiplier, in this case like b0, for example, accept oh wait, never mind. I just solved it myself. Never mind. Never mind. I solved it myself.
Okay. Okay, so basically it's a multiplier. So if you need to multiply xn with a certain number, then you must have this multiplier, and the location of the multiplier, of course, it based on which parameter that we want to multiply with those numbers. Yeah. So if we have xn here, we could you could look the first part here. It is b0 times xn. We already have xn here. You have to multiply it with b0. Then xn must went through a multiplier with b0. So the output here would be b0 xn in here. And then there's a branch here, which is also an xn, but it went through a shift register, which means that the output of this shift register would be xn minus 1. And then it went to a multiplier with b1, and then the output here would be b1 xn minus 1. And then it went through an adder or a summation between b0 xn and b1 xn minus 1. That would result in the output of yn. So we could make this diagram based on the differential equation that you have for your system here. Is there any question, or is it clear enough for you to understand? I think it is clear enough, so I can carry on. For the next realization system, when the differential equation has a different kind than the previous one. So in this case, the output of the system depends not only on the input, but also depends on the previous output. So there will be a feedback from the output, which is feed to the input of the system. So we have xn. So the differential equation is here. Yn equals to xn minus a1 yn min 1. So this is an xn. Yeah, we already have xn here. And then the next one is a shifted version of yn multiplied with a1. Then in here we already have yn. Here yn, and then what is it? It becomes intersection here. Can I call it intersection? This branch where the output yn went to a shift register. Yeah, so it's stored as a shifted version of yn. So it is the previous output value, and then it is multiplied with minus a1 here, and then we sum up with the xn. This will be yn. Yeah, if you could see the multiplier direction of the arrow direction for the output feedback is going to the left. If you compare with the previous example, or what happened to the x, to the input, related to the input, yeah, the multiplier is headed to the right direction, and then for the output, it's in the other way around. It is to show that this is the feedback of the output, and that this is the function which is depend on the input, related to the input. You can see the difference. And then what happens if we have both of these system in our system? So we have the input dependent, and also we have the output of the previous time dependent. Then we could use this example where the differential equation is as the following. So yn plus a1 yn minus 1 equals to b0 xn plus b1 xn min minus 1. So there are an input dependent, and the input also have a memory. The input the system have a memory for the input, and also have a memory for storage of the output. Then what should we do if we have this kind of systems? It is better to make this equation into two separate equations. The first one, you could assume that the right part of the equation here, you could assume that this is y and here. So yn equals to b0 xn plus b1 xn minus 1. And this, you always have to make the differential equation and in this form. So this is the output of the system, yeah, equals to blah blah blah. You always have to make the differential equation becomes the definition of the output equals to the input and minus a1 y and min 1. Yeah. Always make sure that your differential equation is not still in the general form where the output parameter is on everything is on the left and everything related to the input is on the right, but you have to change, yeah, this expression into this kind this kind of expression, yn equals to something, yeah. So you can make sure that the output will depend on everything on the right side of the equation. Why I try to highlight this, because it will be sometimes you become confused when you put this constant value or a1 here, for example, in the multiplier. Sometimes if you don't change this expression, yeah, to here, then you will get the the constant here will have a different sign, yeah, because it changed side on the equation. What you have in the realization block diagram is that you put the value of the constant value here, the sign is associated with the constant value when the equation is already in this form. I just want to stress on that so that you don't make a mistake later when you do some of the exercise or the exam later. Yeah, you only have to write down the constant exactly like what is it in here to here. Then continue to this slide. After you assume that this is a Wn, yeah, you could see that this yn will depend on wn and the shifted version of yn. Yeah, we called this is equation 1 and this is equation 2. In equation 2, yeah, wn is the output of the subsystem 2. Yeah. So in here there is an explanation that the equation 1 is a differential equation for subsystem 1, which has an impulse response which is notated by h1n. And for the second equation, yeah, it is a second subsystem with impulse response which is notated with h2n. So you notice that you have to notice that this is the actual the full differential equation for this system, we try to divide this system, divide it into two subsystems. Yeah, two subsystems. If this system have a impulse response of Hn, yeah, it is divided into two subsystems which have H1n and Hn. Yeah. H1n is related to this differential equation, and H2n here is related to the second equation here. You could see that in the first subsystem, yeah, Yn is the output, yeah, and then Wn here is the input. This is also the input, but this is actually the shifted version, yeah, or we could say the delayed version of the output, Yn. And in the second subsystem, yeah, this Yn is the output of the system, and the input is Xn. This is the input. As you can see, the output of the second subsystem will be the input of the first subsystem. So you could sketch on your diagram. If you have two subsystems, then you could say, oops, sorry, H2n, H1n, and the input of H2n is Xn, and then the output of H2n would be Wn, and the Wn signal here will be the input of the first subsystem H1n, and the output would be N. And then you need to make a diagram based on the equation of the first and the second subsystem. Where in the first one, this is the second subsystem, and this is the first subsystem. This is related to the second equation on the previous slide. Here. Then for H1n is related to the first equation here. Yeah, I hope you could follow this. So we knew that from the first equation, perhaps I will write it down here. We have from the second equation is Wn equals to V0 Xn plus V1 Xn minus 1. Xn times V0 plus V1 times Xn minus 1. That would be Wn. And then the first equation, which related to output Yn, equals to Wn minus A1 y and min. That will be this part. As you could see for this direct form, the second direct form here, for this kind of system, you will need two shift register memory, yeah, for the input here and for the output here, for the feedback of the output here. And then you will need 3 multipliers and 2 adders. It is possible to simplify this system, yeah, if we consider to what is it, to simplify and to have less memory. Perhaps you don't want to use a lot of shift register. In this case, you could simplify this system by making use the property of the impulse response, where it is said that it has a commutative property. So it doesn't matter if you do if you change the order of the systems, and H1n, you change the order to here. So the systems will be like this. H1n first, then H2n first. It doesn't matter, yeah, because we knew that H2n convolution with H1n equals to H1n convolution with H2n. Yeah, this whole diagram can be described as a convolution of the xn with H2n, yeah, and then it is convolution and the next what is it? It is convolute. I don't know the verb for convolution. So we do convolution again with the H1n, then we get the yn. We can change the order if xn, we did this first and then the H2n. Why we did that? Because by changing the order, we could make some reduction of the element that we will need to realize our system. Yeah. So in this draw, you could see that the order already shifted, but this is I think this is wrong. Yeah, it is shifted, and then you could see that we could merge these two shift register, where we used to have two shift register for input and output, and here we could use only 1 by merging these two shift register, and we could save one less shift register than the previous slide. This, we could simplify this into this. Yeah. So it's like merging this shift register, becoming only one shift register, both for storage of the input at the previous one previous sample, and then this is for because the direction is to the left, so this will be related to the feedback of the output, and this one is related to the input xn. So this is the simplified version of the same systems, where we only need one shift register for storage and the same number of multiplier and enter. Because in making a system, usually we always try to save the requirement for memory. Yeah. So our system will be more efficient. So this is the general form of the diagram. Yeah. If we have a differential equation like here, yn equals to minus sigma k from 1 to n, ak yn with k, and so on. This is the output, the part of the output which must be feedback to the input of the system. Yeah? This is the previous output value, and this is the input at currently, yeah, and the previous one. If you could see the drawing here, this left part is related to the input. Yeah? So there is a B0, B1, B2, and so on until Bm, yeah? Because you could see that the sigma here is from k equals to 0 to m, which means the bk here will also act as a constant multiplier from B0 to Bm. And then you could see that there is a shift register here. So you could understood from the draw that in here you will get xn minus 1. And then if you go through another shift register, then it will be xn minus 2. And here you multiply with B2 and sum up with the rest of the signal. Here goes on until m, yeah, k equals to m. So this here will be xn minus m multiplied with bm, yeah, plus everything in between. So this part here is related to this part of the formula. And then the other one in the right hand side here it is it illustrate for the process which is in this part of the equation. As you could see, the multiplier is everything is minus here because of this minus. And you could see also that the A value, the AK value is started from A1 minus A1 and so on until AN capital here, because the K value for the output here is ranging from K equals to 1 to N. And here we always have to be no multiplier for this part, because here is related actually to the A0, right? A0, you remember the equation, this is A0 times Yn, yeah? But if you have to make it, the equation becomes the definition of Yn, then this constant must be become a division of this AK and PK constant on the right side. So you have to move this to remember to do this before you make the diagram, because this A0 in here must be already normalized to this value. And this is we call it direct form 1, or the first direct form structure of the system, where M equals to N. And the simplified version of the system realization is here. You could see that this you could get by changing the order of the system. So as the same as the previous example, you could assume that this is two different subsystems. And you could change the order, where the red part subsystem goes to the left part of the, we could say this is subsystem 1 and this is subsystem 2. Then you could change the order and bring the second subsystem to here. And then you could see that you could save up the memory requirement. We can half of what you actually need in this direct one. Second direct form. Now you could see that the number of the memory storage required for the system could be reduced till half of what we have in here, because we could use less memory, use for both the input and the output system. This is the general form for Dirac form 2. Any questions until this part? This is the last part of the presentation. So if you have any questions regarding what we have discussed today, you could raise your questions now. We still have, I think, half an hour or so.
No question, miss.
Really? No questions? Everything is clear or everything is not clear?
At least for me, it's quite, it's not
Okay.
unclear. It's quite clear, but I'll reread the slides again later.
Okay. Perhaps if you could, I don't know if you are convenient to have books written in English or in Indonesian, but if you more familiar, because I understood that I think you are Indonesian student actually, you could buy the books which written by Dr. Swadi and Dr. Titi. It has an explanation in more details about what we have discussed. Plus, it also have a lot of examples of how you could do the convolution or do the the validation, whether the system is linear or not, and whether the system is down varying or not. So you could actually make use of these books if you need it, of course, because sometimes it is difficult to understand some material only based on the slides or only based on what I have explained it to you. You need to have a lot of exercises to really understand and to really know what you will have to do, or you have to calculate it in this method. Okay, wait, I need a moment to clear the area. Yeah, sorry for the interruption. Okay, because no questions, then I will raise a question for you. For example, if we whiteboard this. Okay, because you don't have a questions. And I will ask questions. For example, if we have a discrete signal, uh, xn, oops, that's the notation. So the xn will be can you sketch a signal which is xn minus 2 xn plus 2, what else? xn, sorry, not xn, but x minus n plus 2. And the last one would be x to n. So which one of you would like to try to solve the first part?
Draw the diagram, right, Miss?
Yes, you
Oh,
could.
I think I could try.
Yeah. Feel free to use the, I think I already give permission for annotating. And who will do the next one?
Me, ma'am.
Okay. The signal, yeah, I need to look the signal.
Am I doing it correctly, Miss?
You are making the diagram for the realization of the system, but it is not the questions that is asked because what we see here is actually a discrete time signal xn, and
Oh.
then I would like to know if you understand or if you could make a sketch of the signals when it is xn minus 2 and the other one is xn plus.
Okay, I misunderstood the question.
Okay.
Minus 2. Oh. Oh, wait, I don't need to do that.
And who will do the C and D? Yeah, the B one is correct. Yeah. So the B one is actually is the signal will be the same exactly as xn. It's only shifted 2 samples to the left. And for A is actually correct also. Difference is just the signal is shifted 2 samples to the right. And how about the C one? Nobody know. It is like you reflected the signal, the xn is reflected to 0, yeah, and then shifted to the
Right, to the left.
left or right.
To the left.
Are you sure? So the x minus n, would draw first x minus n. This would be x minus n. And what would be x minus n plus 2? That would be shifted to the
Left, right? It's to the left. I mean, it advances by 2 places, right?
What's your reason that it should be shifted to the right, to the left?
To the left.
Yeah. What
Because-
makes you said that it should be shifted to the left?
Oh wait, never mind. Oh wait. Plus 2. Yeah, I think so because it's supposed to be minus n. Oh, because it's it 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 starts earlier by -2, right? Because if I'm not mistaken, the original equation is n. No, wait, what? Wait, I need to remember again.
What we have on the slide is that if we have x n minus